This is a demonstration of the real-time anomaly detection in HDFS logs. That is the topic of the thesis. So this demonstration will walk through the raw data that we're dealing with, how the model is trained using an embedding model, specifically the SBOT model, then how we utilize a unique ensemble model to give the final predictions. Then we walk through how the model is evaluated in varying testing conditions such as different percentages of anomaly injection. Finally, we prove the real-time capabilities of the model on an actual HDFS cluster in AWS EMR. So moving on, this is the log. This is the log file that is obtained from LogHub. This is the raw HDFS dataset. So this dataset consists of the timestamp, the log severity level, the component, and the raw log string. Now every log string consists of a unique consists of a block ID on which the block operations have taken place. The second file that we get from the dataset is the anomaly labels. Now the anomaly labels here are at a block level, not at a line level. So this is challenging because the solution aims to be real time and it needs to detect anomalies at a line level instantly. So now every block can be present in multiple lines. So as per the dataset, the anomaly ratio in the dataset is 2% out of the 5,75,000 log entries. Then we move on to the parser. Now the parser creates templates out of the logs just to find the patterns that exist in the logs. So this is a Drain3 parser. It's an open source parser. Now this parser creates templates and template IDs. So here we see it has stripped out the dynamic fields such as the timestamp, the block ID, the source and destination IP addresses just to get the patterns. Now this is beneficial during exploratory data analysis because we know which are the most frequent log patterns that are occurring and what is the anomaly rate in those patterns. Finally, we have the structured logs. Now the structured logs contain the original log message followed by the log template ID, the template to which it matches, and the dynamic components of the log string are in a separate list. So this helps to train the model in a more efficient way. Moving on, we covered the dataset and how the dataset is structured into templates. So now we'll cover how the model is trained. So essentially the training module consists of an anomaly trainer script, a line level loader utility, wherein the anomaly trainer calls in the line level loader utility and assigns a label, either anomaly or not anomaly, either 0 or 1, to each individual HDFS log line using the dataset, using the labels that are already available at a block level. Now the labeled logs, they are passed on to an SBOT embedding model, which is the all-mini LM L6v2, and the embeddings are generated and passed on to an ensemble training model. Now the ensemble training model consists of the decision tree, the vector similarity, stochastic gradient descent, and the multi-layer perceptron. Now each of these models perform their own predictions on the validation dataset, and depending on the performance of the models on the validation dataset, the F1 score, each model is assigned a weightage in the final ensemble model, and the final ensemble model is then stored as an artifact and which is used during the anomaly evaluation at the inference stage. So this is the repository. Now the repository is structured in a way that each component of the setup has its own folder, so that is easy to maintain and understand. So here we have the training folder. The first component is the HDFS line level loader. So the purpose of the HDFS line level loader is to assign a label to an individual log entry. So the way it does is it follows a two-strategy approach. It acts upon the parsed HDFS logs that are generated by the parser, and it essentially looks for the anomalous keywords, the frequent keywords that often occur in anomalous blocks, and then it has a strategy wherein if that keyword occurs in the log and if the block of the log is marked as anomalous, then the line is also marked as anomalous. The second strategy that it performs is that if there's a rare event in the log that that is very rare, in the bottom 10 percentile, and also if the block of the if the block is also marked as anomalous, then the line itself is marked as anomalous. Now the train line level ensemble v2, what this does, it calls upon the HDFS line level loader to get the line to get the line level labels, as well as the raw HDFS line, raw HDFS log line, and then it passes it on to an embedding service. Once the embeddings are generated, it takes it into batches of 10 each, batches of 100 each. So this is the training data set. So this is the training structure, I mean. So we take into consideration 200,000 total samples from the HDFS logs. The training consists of 1,60,000 samples, the validation consists of 40,000 samples, and the anomaly ratio is 0.22%. So the anomaly ratio falls from 2% in the original HDFS dataset, and when we convert it to a line level approach, it comes down to 0.22%. So it is a fairly imbalanced dataset that is obtained. So here we have the hyperparameter tuning of each of the individual models. Which is decision tree, multi-layer perceptron, stochastic gradient descent, and the SGDClassifier. And then essentially there is also a unique approach for the quadrant similarity detector. So the way it works is it takes into consideration the normal embeddings which are not anomalous, and the way the logic works is that if any embedding has a certain distance or it exceeds a certain distance threshold from the normal embedding space, it is considered as an anomalous. So it creates it takes into consideration 10,000 normal embeddings, 10,000 normal embeddings of normal logs, I mean, and what it does is it calculates the best cosine similarity distance that gives the best F1 score upon validation. So it's better illustrated by this screenshot here. So you see it takes into consideration the threshold starting from 0.3 to 0.9, and threshold cosine similarity of 0.5 gives the best F1 score, and then this is chosen as the as the final threshold. So moving on, then the model is trained and the results of the model are stored in a separate folder. So here we see the results, the model, the precision recall, F1 score, and its weight. So the way the weight is assigned is that the model which gives the best F1 score gets the highest rank, and it gets an associated weight, a proportional weight for voting in the line level in the ensemble model. And then the model is stored in a job-lib format, and this job-lib format model is loaded by the anomaly detection service to do the anomaly detection in real time. So this is the output of the hyperparameter tuning. So it trains a decision tree, it gets the best hyperparameters. The output shows the precision recall and F1 score of each of the ensemble models. And here again, this is the final ensemble v2 model performance. So we see that the decision tree has an F1 score of 0.122, and it is assigned the lowest weight. The highest weight is granted to the multi-layer perceptron and the quadrant similarity. So this is the final ensemble model weighting and the ranks depending on the F1 score. And this is further explained in the thesis. Now we move on to the model evaluation phase. So now that the model has been trained, the model needs to be evaluated on varying anomaly injection levels, meaning that the model will be trained against varying percentages of anomalies that are there in the logs. So to do this, it's a two-phase approach. The first phase is the development of an anomaly detection service. So the anomaly detection service loads the trained ensemble model that was generated in the training phase, and it takes, in simple terms, it takes each individual HDFS log entry, and it performs the weighted ensemble voting. It generates the predictions, stores the prediction results in cache, and it also stores the log anomaly counts and the performance and accuracy metrics in an SQLi3 database. And upon anomaly detection, it will send the stats to Grafana, where the anomaly trends can be visualized and be alerted. So moving on to the code. So here is the anomaly detection service Python script. So as it was stated, it loads the trained ensemble model, the model artifact, and it listens to and it listens on Kafka, on the Kafka topic logs. So essentially, any log stream producer will produce logs on this logs Kafka topic, and the anomaly detection service will consume the logs. So the way it works is, once it consumes the logs, it does a query to the quadrant database, to the quadrant vector DB, and it tries to see if an embedding of the log is already present. If it is not present, it falls back to the embedding service to generate the embedding. Once the embedding is obtained, it does a weighted, the ensemble model performs a weighted prediction, and the final results are stored in cache. So next time the log entry comes in, if the prediction has already been made, it does not have to go through the entire loop of querying for the embeddings or generating the embeddings. It will take the cached result. So the way it works is like this. Yeah. So the scoring, the anomaly detection service, it loads the ensemble model. It gives the output that these are the weights of the ensemble model, and once it starts, let's say an individual, let's say it found this particular HDFS log entry. On evaluation phase, this is the predicted label and this is the actual label. It caches the result, and then the next time it gets a cached hit. So it uses the cached result, and if the similar log entry is generated, so this kind of reduces the resource usage. So now to evaluate the model using the anomaly detection service, there is an anomaly evaluation, there's an anomaly injection loader that is created. So the anomaly injection loader would essentially go through the parsed HDFS logs. It would generate the line level labels similar to the previous loader, and it would create a log, and it would create JSON files of 10,000 samples each, with varying anomaly injection ratios. So this is 5%, 10%, 15, 20, and 40%, meaning that each of these individual files, they have varying anomaly injection levels. So this is crucial to test the model performance in these kind of scenarios, which could occur in real world use cases. So these files are stored here, and then we have an anomaly evaluation Python script that would take any of these files as an argument. It would just expose those log entries to the Kafka as a Kafka producer, and then the anomaly detection service would listen to would consume the Kafka logs and would make the predictions. So the results of the predictions are stored in the anomaly evaluation results. So each of these are stored as a separate file when the model is run, and these are the screenshots of the anomaly evaluation results. So here you see that let's say at 15% of anomaly injection, this is the accuracy, this is the performance, precision, accuracy, precision, recall, and the F1 score. Now all this has been accumulated in a tabular format for better viewing. So we see that in spite of varying anomaly injection levels, the F1 score remains consistent. So this is of particular use case. This is particularly beneficial in real world scenarios, wherein you may have anomaly ratios as low as 1%, or it can be as high as 40% or 80%, 100% also. But the F1 score, which is a balance of accuracy, which is a balance of precision and recall, that has to remain consistent. And here we see the average processing time. So the average processing time is in milliseconds for each individual log entry, and as the cache hit ratio increases, the average processing time decreases. So this is also one of the benefits. and the logs of each of the Python scripts, they capture all this in detail, the total predictions, the average processing time, and they store it in the CSV files for each of the log runs. So this is of crucial importance, wherein we get confidence to deploy our model in the cloud. Yeah, thank you. This how the setup has been deployed on an actual HDFS cluster in AWS. Before I do that, I'll showcase what is the local setup. It has been done entirely using microservices and Docker. So there's a Docker compose file, and all of this has been created: the Kafka, the SBERT embedding service, anomaly detection using anomaly visualization using Grafana, the Vector DB quadrant, and the Redis cache. All of them are locally running using Docker, which is generated using the Docker compose file. And now the benefit is that since we have all the infra as a Docker compose file, it can also be deployed in other environments such as a cloud environment or any environment that of the choice. So this is the deployment to an AWS Elastic MapReduce cluster, which is essentially an HDFS cluster running with a data node, running with a name node and some data nodes. So this is the setup that resides on the data node. Now Hadoop emits and stores its logs in the var log HDFS log stream. To process this in real time, there's a log stream processor that filters and pre-processes only the block level operations of HDFS. So let's say it's continuously Hadoop is continuously sending logs on var log Hadoop HDFS directory consisting of heartbeats and other operations. They are pre-processed and filtered and are passed on to a Kafka broker. Now the Kafka broker has two consumers. One is a Spark job and the other is the anomaly detection engine. So the Spark job takes in each log entry. It generates the embeddings using the SBERT embedding service, and it stores the embeddings in the quadrant vector DB. Now the Spark job is intelligent enough to identify that if there are any duplicate log entries coming in, it will query the quadrant vector DB and it will avoid storing them again, which will be shown in the demonstration. The second consumer is the anomaly detection service or the anomaly detection engine. This particular this actually performs the predictions. So it retrieves the equivalent embeddings of the log entry, and it performs the predictions. If the embeddings are not found, it does a fallback to the embedding service. So this ensures that this fallback mechanism is critical because it ensures that if the vector DB is not available or if the embedding is not found, the service can continue as usual. Now, once the anomaly detection service, once it gets the embedding, it performs it loads the trained ensemble model and performs a weighted voting, and it stores the prediction results to Redis cache. So if the similar log entry appears again, it does not have to go through the entire embedding process, and it also stores the system stats in an anomaly metrics database. The system stats can be the accuracy metrics, the system performance, average response time, the predictions of each model, the weighted voting results, and all of this can be visualized using Grafana dashboards, which take the SQLite the SQLite data source as its source, and these are useful for an end user or the system administrator that wants to visualize and do some alerting based on the anomalies that are being generated. So now we'll just take a quick look at the code. So this is the code in the cloud deployment, which are exclusive to like some Python scripts which are exclusively developed for AWS EMR. So this is the HDFS preprocessor that we spoke about. Now the HDFS preprocessor preprocesses the logs in var log Hadoop HDFS directory, and it publishes the logs on a Kafka producer. So this is what this is the log directory in var log Hadoop HDFS, and essentially before we start, we had to make the log level as debug. So that it captures maximum detail and it captures the block level operations also, which is what we are aiming for. And these are some of the anomaly scenarios. So the scenario that I will focus on the demonstration is corrupting a block and trying to retrieve corrupting a block and trying to retrieve a file from the block. And these are all the other anomaly scenarios for which the equivalent HDFS commands were developed. So now this is the EMR cluster over here. So the EMR cluster consists of an HDFS consists of Hadoop running on 3.4.1, and it has one primary node and one data node. Previously it had two data nodes, but we reduced it to one data node for resource savings and cost savings as well. Now these two are running on EC2 instances. So I SSH into each of the EC2 instances, and now I'll show the demonstration of how it works. I have SSH to the data node of the HDFS cluster, and here I have the preprocessor Python script. What it does, it continuously listens to the var log Hadoop HDFS log file. If any new entry is generated, it does the preprocessing filtering and passes it on to Kafka. So let's run this. It's continuously watching the file, and it is streaming the logs to the Kafka topic logs. So over here we see that it has read 3 but it processed 0, and it has sent 0 to Kafka. So nothing has been sent to Kafka yet because everything has been filtered out, because there are no block level operations currently. So here I will start the process to consume the logs that are sent to Kafka using the Spark job. So this Spark job will essentially create a logs embeddings collections in quadrant, and it will call the embedding service and store the embeddings in quadrant. So now it has started looking for the logs, but none have arrived yet because there are no block level operations currently. So now I have coming to the anomaly detection service. So I will restart the anomaly detection service to clear the Redis cache and kind of start with a clean slate, and I will tail the anomaly detection service logs. So these logs will tell us how the predictions are taking place. Yeah. So it says that 6 cache results have been cleared, and it is also listening on the Kafka topic logs. If you see here. Now I'm coming to the name node. So on the name node, what I have done is I have corrupted the block of this test file 3, and now I will try to catch the file. So this will generate some block level operations which will be caught by the preprocessor, and it will be sent to Kafka, and the two consumers, which are the Spark job and the anomaly detection service, they will consume the logs. So let's see how it's taking place. So if we see here, it says now 14 process. So this particular command that I ran generated 14 operations, and 14 have been sent to Kafka. And if you see, Quadrant has also processed these 14. Spark also has processed these 14 log entries, and the embeddings have been stored in Quadrant. Now coming to the logs. So here the logger has been as detailed as possible for the anomaly detection service. So I'll just do grep with ingested. So over here now we see this is an anomalous log. So it says it has ingested this. So it says it has ingested this. It has tried to find the particular embeddings in Quadrant, and it was not able to find it for some reason, so it is falling back to the embedding service. So this shows the fallback mechanism, and then this is the weighted voting result. So it says that okay, decision tree gave a vote of 1, MLP also gave a vote of 1, SGD and quadrant similarity did not said that this is not an anomaly. So the final score is 0.51, which is above the threshold that is set up for 0.4. So for this particular, this threshold can be set in the anomaly detection service Python file, and it has cached the result for this particular log entry now. So the next time this log entry comes, it will not have to do the embedding once again. It will store, it will use the cache result. So if you see here, it's over here it's using the cache result. So if I run it again, if I run the same command again, it will use the cache results again. So this also avoids regenerating the embeddings or looking up into quadrant each time. Now there are some I'll just close this, we don't need this now. So there are some API calls that can be done to check the health of the anomaly detection service. I'll close this as well. So since the anomaly detection service is the core, so here we see that these are the 72 anomalies, these are the full stats that are obtained, and here also we see the breakdown of the anomalies. So if I do here, so over here we see the timestamp, the decisions. So basically all the verbose logging, all the verbose information that is stored can be retrieved using these API calls. We also see the stats of what's happening. So here we see the total anomalies predictions are 28, the anomalies detected also 28, the cache hit, cache miss, and the Redis operations. And here we get the cache stats. So yeah, so this is the cache hit rate, which is 78%, and these are the total cache operations, and these are the cache entries currently since the cache was cleared. And here we get the model info. So this is the model, these are the model weights, these are the traditional models, and these are the model weights. So quadrant similarity is 0.414 and MLP is also 0.414, and the decision tree and SGD have a lesser weight because during the training phase the F1 score was the least. So essentially now the anomalies can be visualized using Grafana. So Grafana is the tool, so we can select the time range, and basically I have created some dashboards here. The first is the system overview dashboard. So it says that currently in the timestamp 72 anomalies were detected. The average processing time was 47 milliseconds. And let's say if I try to generate more anomalies, so I'll do this, I'll keep doing this, and it will essentially yeah, so if I keep repeating this anomaly, as long as it is cached, the size of the total anomalies will not increase. But if I clear the cache and if I restart the scoring service, and if I regenerate the anomalies again, this count is going to increase. So this also helps to avoid like too many excessive anomalies. You know, if an anomaly is cached, that means it has already been detected and it has already been observed by the system administrator. So here we see the average processing time. Here we see the average processing time, the anomaly rate, the total records, and here for each these are the recent anomaly detections. So over here for this particular one, you can see the average processing time is 40 milliseconds. It was an anomaly, and this was generated by the Kafka stream. Similarly, there's a new dashboard called the model performance dashboard. So the model performance dashboard essentially takes a look at the decision tree voted the percentage classification of the anomalies. So the decision tree said okay, 50% of the log entries are anomalies. MLP said 100% of the log entries that coming in were anomalies. SGDClassifier and quadrant similarity did not classify any log entries as anomalies. And here we can see the RD performance bucket as well as the anomaly votes and normal votes. So quadrant similarity. So this is the snapshot of the demo. Of course, in the demo we were generating anomalies. We did not generate any normal log entries. So MLP is performing well in that case. So okay. Now I just want to show in the Grafana how the real-time system looks. So now that I've restarted everything, I'm also restarting my log processor, and I'm doing a corruption. So and now it's yeah. So if you see here, it is found the similar vector embeddings this time, since it was available in quadrant. Previously it was not available in quadrant, so it did a fallback to the embedding service. And now if we go back and check the system overview dashboard, you see I refreshed it and it's 78. So when I generated more anomalies, it went from 72 to 78. So this is a real-time dashboard. After I refresh, it will continuously keep increasing the anomaly count as long as it is not cached in Redis. So yeah, this was a short demonstration of the real-time anomaly detection approach, and we can also keep enhancing these dashboards and keep trying to make the system more scalable and more intelligent. Thank you so much.